Let's take a look at vertical limits. Here's a graph of the function 1 over x minus 2 squared. First off, what's the domain of this function? If you'd like to review domain and range instead, then click down here. Right, the domain of this function is all values of x except for 2. If you were to plug in a 2 for x over here, then you'd have 1 divided by 0, which is not defined. So while 2 is not in the domain of this function, let's look at what happens when x is near 2. How would you describe what happens to this function as x gets closer and closer to 2? Exactly. F of x is getting really big as x gets closer and closer to 2. It looks like this line, x equals 2, is a vertical asymptote for this function, meaning the function keeps getting closer and closer to this vertical line as f of x gets bigger and bigger. But just how big does f of x get? Let's find out. We'll be using this interactive graph to see just how big f of x gets as x gets closer to 2. We have a vertical tube here centered at x equals 2, and you can make the tube wider and narrower by moving these green circles to the right and to the left. We've labeled the width of the tube using the Greek letter delta, and the precise width of the tube is shown over here. There's also a horizontal bar here whose height we'll be calling n. You can change the height by dragging this purple circle up and down, and the exact height of the bar is shown over here. You can also move up and down the graph by dragging the graph itself. Let's set the height of the bar to a specific number, like 4. Notice that if we make the tube narrow enough, every part of the function inside the tube is above this bar. When the function inside the tube is always above the bar, the tube will turn blue, like this. So inside a tube centered at 2 with a width of about 0.5, f of x is always greater than 4. Let's set the bar a little higher. What happens if we set n equal to 10? How narrow does the tube have to be, meaning how small does delta have to be, so that the function inside the tube is always greater than 10? Exactly. When n equals 10, if delta is less than about 0.3, then the function stays above the bar inside the tube. What happens if we make n even bigger? When n equals 25, how small does delta have to be so that the function is always above the bar inside the tube? Right, when n equals 25, if delta is less than about 0.2, then the function stays above the bar inside the tube. Let's try one more bar height. When n equals 100, how small does delta have to be so that the function is always above the bar inside the tube? So it looks like no matter how high you set the bar, if x is close enough to 2, meaning the tube is narrow enough, f of x stays above the bar inside the tube. Let's rewrite this statement a little more mathematically. Saying no matter how high you set the bar is the same thing as saying that the bar can be at any height n greater than 0. So n can be small or n can be as large as you want. For any value of n, if x is close enough to 2, f of x stays above the bar. And saying f of x stays above the bar is the same thing as saying that f of x is greater than n. So now let's take a look at this statement in the middle. Remember, you found that for any value of n, you could find a tube width, which we called delta, so that f of x stayed above the bar inside the tube. So in terms of delta, how else can we say that x is close enough to 2 for f of x to stay above the bar? Precisely. So let's put everything together. For any value of n greater than 0, where n is the height of this bar, there's a value of delta, which is the width of this tube, so that when x is inside the tube, meaning 2 minus delta is less than x, which is less than 2 plus delta, f of x stays above the bar. That is, f of x is greater than n. So this statement says that no matter how high you set the bar, if you set x close enough to 2, you'll pass that bar. This statement has a lot of parts, and each requires a bit of thought. In calculus, this statement can be summarized by this equation. These two statements mean the same thing, but this one is a lot shorter to write down. You can read this as the limit of 1 over x minus 2 squared as x approaches 2 equals infinity. This means that as x gets really close to 2, this function goes off to infinity. These two expressions here are completely equivalent. So while this function is not defined at x equals 2, you've shown that the function gets infinitely big as x approaches 2. With the interactive graph, you were presented with different bar heights n and asked to find tube widths delta so that f of x was always above the bar inside the tube. Now, to make sure that you can find an appropriate tube width, no matter how high we set the bar, we'll want to find a precise relationship between the tube width delta and the bar height n. Are you ready to figure out this relationship? If so, then click here. If you'd like to skip ahead to other examples of vertical limits, then click here instead. Good choice. Let's see how delta and n are related. Let's take a closer look at this inequality here. F of x is greater than n, which means the function is above the bar. In this example, we said the function f of x equals 1 over x minus 2 squared. As x gets close to 2, this function gets really big. Let's see how close x has to be to the number 2 so that this function is greater than n. To solve for x here, we can multiply both sides by this denominator x minus 2 squared and divide both sides by n. So basically, we can switch these two parts of the inequality. That means that saying f of x is greater than n is the same thing as saying that 1 over n is greater than x minus 2 squared. So how close does x have to be to the number 2 for this inequality to be true? In other words, what's delta in terms of n? This is a tough question, so if you'd like to work this through step by step, then click down here. Okay, let's do this. We have x minus 2 squared on the right, so to find an expression for x, it's probably a good idea to take the square root of both sides. Now things get even trickier, so we'll proceed very carefully. You might be tempted to cancel the square root and the square over here, but that only works when what's inside here, x minus 2 in this case, is positive. If that's confusing, don't worry. Let's try an example. Try evaluating these two square roots over here. Remember to evaluate them step by step, and also remember that the output from the square root function is always positive. Exactly, the square root of 3 squared is 3, but the square root of negative 3 squared is also positive 3. By squaring and then taking the square root, we lost the minus sign over here. So, keeping in mind that the x minus 2 here could be positive or negative, what's an equivalent expression for the square root of x minus 2 squared? Is it x minus 2, negative x minus 2, or the absolute value of x minus 2? Precisely. So let's replace this expression on the right with this equivalent expression. So we started with this inequality that said the function is above the bar, and we found this equivalent inequality that the absolute value of x minus 2 is less than the square root of 1 over n. The absolute value function gets rid of minus signs, so the absolute value of x minus 2 represents the distance between x and the number 2 on a number line. So let's draw in a number line, making sure to include where x equals 2. Let's also add 2 more points, where x equals 2 minus the square root of 1 over n, and where x equals 2 plus the square root of 1 over n. Which part of this number line does this inequality, which says that the distance between x and the number 2 is less than the square root of 1 over n, represent? Correct. This inequality is satisfied when x is in this region here, between 2 minus the square root of 1 over n and 2 plus the square root of 1 over n. So when x is in this region here, the function is above the bar. That's exactly what we meant by saying x was in this region here, between 2 minus delta and 2 plus delta. So for this function, 1 over x minus 2 squared, delta equals the square root of 1 over n. For any bar height n, when x is between 2 minus the square root of 1 over n and 2 plus the square root of 1 over n, the function is above the bar. So you know for sure that no matter how high the bar is, you can find a narrow enough tube. Whatever height n I pick, you can set the tube width to be the square root of 1 over n, and you know the function will be higher than the bar inside the tube. At this point, let's look at a few more quick examples of vertical limits. So far we've been looking at the specific function 1 over x minus 2 squared. Now let's look at the generic function f of x. And instead of looking at the limit as x approaches 2, let's look at the limit as x approaches the generic x-coordinate a. That means we also need to change the 2's over here to a's. And here's the general statement for a vertical limit. If this statement is true about a function f at an x-coordinate a, then we can say that the limit of f of x as x approaches a is positive infinity. But what if the limit is approaching negative infinity? Here's an example of a function that seems to be approaching negative infinity over here when x equals a. Rather than setting the bar higher and higher, we're saying that no matter how low you set the bar, the function always goes below it. So which parts of this limit statement should we change so that it says the limit is negative infinity? Exactly. Instead of having n be greater than 0, we have n less than 0. And instead of saying f of x is greater than n, we're saying f of x is less than n, meaning the function is below the bar. So this is the statement that means the limit of f of x as x approaches a is negative infinity. Let's look at one final example. Here's the function f of x equals x squared. As x gets really, really big, what happens to f of x? Correct. And here's how we can write this limit. The limit of f of x as x approaches infinity is infinity. When you write positive infinity in limits, sometimes you'll see a plus sign and sometimes you won't. But these both mean positive infinity. And here's the equivalent way to write this limit. We're saying that for any bar height n, you can find a value of t so that for all x greater than t, f of x is above the bar. That is, f of x is greater than n. So no matter how high you set the bar, the function eventually passes the bar and stays above it.